This lesson is about diffraction. Learning objectives. Define diffraction of a wave. Give some examples of diffraction. Learn about the Ripple Tank Lab. And draw some diffraction diagrams. This picture shows a traveling wave. The white lines are the crests and the dark lines are the troughs. Remember, the distance between crests is the wavelength. Diffraction is referred to the bending of waves as a result of passing through an opening of a barrier. The shape of a diffracted wave is affected by the size of the opening or slit. Diffraction is most noticeable if the opening size is smaller than the wavelength. If the opening size is greater than the wavelength, diffraction is difficult to detect. Diffraction of waves changes the direction of its propagation. However, most of the variables of a wave are not affected. Wavelength does not change. As you can see, the distance between the crests on both sides. Frequency does not change. The number of waves that pass in 1 second is the same. Therefore, the speed of the diffracted wave does not change. The amplitude of a wave decreases after diffraction. The diffracted wave loses energy to its surroundings. Diffraction, we can observe diffraction in water waves. For example, in this picture, this is an upper view of a beach shore showing ocean waves passing through a barrier gaps and creating semicircular shape. Diffraction can also be observed in sound. Here we have Jill and Jack. They cannot see each other because they have this barrier between them, but they have an opening between this wall. There is a doorway. When Jill speaks, the sound waves is going to be travel and is going to pass through this opening and diffract. The diffracted waves is going to reform the sound waves so Jack can listen what Jill is speaking. Another example of diffraction is the diffraction of light. So we can use diffraction to understand how the white light is composed by all colors of the rainbow. Diffraction around the corner. An example is sound. When sound waves reach a corner, the edge causes waves to curve. This is a form of the diffraction of sound waves. Another example of diffraction going around a corner is the highway noise barrier wall, which is a solid obstruction built between the highway and the homes along the highway. This wall reduces the loudness of traffic by as much as 1/2. Diffraction of light. We are going to study and understand the color separation screen, also called spectra diffraction grating. So we are able to see the colors of the white light through this screen. So how is this possible? We can use this screen to observe the separation of light using diffraction. To start with, remember that a single slit produces diffracted waves as shown. A diffraction screen has many slits, many openings like this. The slits are equally spaced parallel grooves that allowed light waves pass through and diffract, like this. This is the light waves that is going to pass through all these many slits or openings. So when all this light pass through those slits, they recombine on the other sides, crests with crests, troughs with troughs. Their recombination create some wavefronts with the same wavelength. In this case, in this example, the wavefront that was created, the wavefront here we can see from the top of those waves, the crests. This wavelength is the size of the blue light. So a blue light range here from 420 to 450 nanometer. Nano is 10 to the 9 power. So here is the section of the spectrum, the EM waves. This section is the infrared, this is the visible light, and this is the ultraviolet. We are going to be looking just this section right here that corresponds to the visible light, which ranges from 400 nanometer violet to 700 nanometer, which is the red color. Now, this other example of the diffraction when light passes through all these slits, the recombination is going to produce a wavefront that wavelength is the size of the red light, which is 700 nanometers. Now let's replace these wavefronts with a diffracted ray, like this. So this blue ray is representing this diffracted wavefront. And then we have between blue and red, we have all these colors, green, yellow, orange, just like it's showing here. Blue, green, yellow, orange, and red. So the diffraction waves, they are going to recombine on the other side as they pass through all those little tiny gaps and form different wavelengths. They are going to combine and form one color of light because the size of the wavelength. Now what happened here in this picture that we see the white light in the center and we see the colors on the left side and we see the same color on the right side, like they are mirroring each other. So what happened is we have here the white light and we have on this side blue to red in this same sequence from the other side, blue to red. So that's why you see two sequence on both sides of the white light. So diffraction can explain how we can see different colors by looking the white light through a diffracting paper. Now let's talk about the ripple tank lab. So a ripple tank is a shallow, transparent tank of water using physics labs to demonstrate properties of waves, including reflection, refraction, and diffraction. This is the wave generator. Oscillates on the water surface, creating ripples. And the ripples can be observed on the white paper placed under the tank, because this light on the top of the tank is going to produce an image on this white paper. So we can observe all the patterns of the wave by looking its image on this paper. The wave generator have attachments that produce different types of ripples. It can be measured using a simple ruler and a stopwatch, and we can measure here wavelength, frequency, and speed of a wave. Now, for the ripple tank experimental lab, we are going to observe straight waves, reflection from a diagonal barrier with different opening size and diffraction shape, circular wave reflected from ripple tank walls. Let's look one by one from next slides. So this is a picture and how I set up this lab in my physics classroom. So we have here some trace that is the tank is transparent. I place water here. We have the light above, and we have the white piece of paper at the bottom. And we have here the wave generator, and we have the power supply, and also we can change the frequency that the wave generator is making the waves. Let's take a closer look. So this is the wave generator. And here is the attachment that makes the plane type of waves. This is another view of the wave generator connected to the power supply. And we can use this power supply to create different frequencies. And here we have that straight attachments that make plane waves. This is a barrier, and this is the white paper. So below you can see it's transparent. So the light passes through and reflects the image on the white piece of paper at the bottom of this tank. So let's look at our first example. So we create a straight wave. So no barrier, nothing. Just start the wave generator and it starts to create those ripples on the surface of the water, and we can observe on the white piece of paper. We place this ruler because we can actually measure the wavelength of this wave that was generated by the wave generator. So just take a look here. Okay, so that, and the first thing we need to do is to determine the wavelength. So those white lines, they represent the crests of the wave. And we know that the distance between two crests is the wavelength. So we're gonna mark here those 2 points, and then we are going to measure the distance between those 2 crests. So one is, this is 7.5, this is 9.5, so the difference is 2 centimeters. So let's say that we want to make sure that is acceptable number. So you can kind of pick another location. This right here is the distance. So that is 19.5 minus 7.5 is 12 centimeters. And now I need to count how many white lines I have between those 2 points. So it will be 1, 2, 3, 4, 5, 6. So 12 centimeters divided by 6 wavelength. So each wavelength is 2 centimeters. So that is a very good number. Now to determine the speed of this wave, we have the wavelength that converting to meter is 0.02 meter. But now I need the frequency. To find the frequency, I need to time how many waves pass in 1 second. So let's say that I run something like this and I count how many pass in 1 second. So I had in this case 15 crests pass in 1 second. So which means that I will have 15, my frequency is 15 cycles per second or 15 hertz. So when I make the substitution, my velocity of this wave is 0.3 meters per second. So we can find all the variables of a wave just by using a ripple tank. All right, so now let's use another feature of this ripple tank to study the reflection when a plane wave hits a diagonal barrier. And let's prove that is obeying the law of reflection, which states that the angle of incidence is equal to the angle of reflection. So here is the white paper, and we are going to generate some waves. So do you see that is kind of, there are some square going on here and some like shaded area. So what happened is those square, the wave, they are coming. So these are representing the coming waves. So when hit the barrier, so we need to define the normal line in order to reflect the wavefront. So we define here the normal line will be normal to the barrier, right? So we have one here that is come and reflect back. The next one the same, it's here, and this reflects back, and so on. So that way, that's why you have that square area all over this section, because you're observing reflection. So to see a little bit better, let's take this picture and flip like this. So let's flip this picture and let's try to find all the terms that when we learn reflection of a wave. So you need to define our solid barrier, which is this one here, is the interface between the water and the triangle acrylic. And now we have all these wavefronts. The red one is going to be replaced by the incident ray. We need our normal line that is perpendicular to the barrier. And now we have our angle of incidence. This angle of incidence must be equal to the angle of reflection. And now we can replace with the perpendicular ray, reflected ray that along with the reflected wavefront. Okay, that's quick. So this is from our lab. We could verify the law of reflection as well. Okay, so this one, we are going to create a barrier for the plane wave that is going to be generated by the plane attachment here from the wave generator to hitting the water, hitting the surface of water and create all those ripples. They are straight. Now we are going to create a barrier and observe how this wavefront is going to pass through this barrier. So here we have 3 sizes, three gaps with 3 different sizes actually, very small, medium, large. And what we observed was I don't have the picture of the wave, but what happened here is the diffraction is more noticeable when the gap is smaller than the larger one. The larger one was hard to see, but this one was very easy to study and actually measure the wavelength of the diffracted wave and compare with the wavelength of the upcoming wavefront, and we could verify they have the same size. Now, this will be the last one, a circular wave reflected from ripple tank walls. To do that, this tray that I select is circular, is not the square tray. This is a circular one, so students can see better. So what happens is when a drop hits the water, is going to create a different pattern. Now, if you look here, this attachment create a single circular wave. They interact with the wave that is being controlled by a student with a pipette. So they interact with each other and they interact with the walls of the tank, creating this pattern. So this is the reflection of circular pattern is not straight. They come back the same way they when they hit the wall, to prove that the diffracted wave has the same wavelength of the one that was generated. Okay, in summary, the shape of a diffracted wave is affected by the size of the opening or slit. So if the opening is smaller than the wavelength or about the same size, so we can notice more. If the opening is larger than the wavelength, it's hard to notice the effect of diffraction. Another cool feature is that wavelength, period, and frequency, they don't change during diffraction. However, the amplitude decreases because the wave loses energy to its surroundings. So the amplitude is related to wave energy. We study the sound waves. So sound waves can be diffracted by a small opening or from a barrier, a wall. Likewise, light, water, and sound, water, and light, they all have the same properties of the wall. And I mean, not the wall, but diffract from a corner. The ripple tank lab, you when you did your straight waves, so you could use all the information to calculate the speed of a wave, and we could verify the reflection of water, and we could verify the diffraction of water as well, diffraction of wave, and the circular wave reflected from ripple tank walls. This lesson is highly illustrated with many pictures to help you to understand how diffraction works and all the properties involved with different types of waves. And I hope that you found this video helpful, and thank you so much for watching.